Hello, this is our 152 design project, and we chose to analyze the stresses, frequencies, and fatigue of a quadcopter to potentially come up with a better designed product. My name is Erick Contreras, and the other members of the group include Herman, Cristian Hernandez, and Sam Ocampo. Specifically, we will be analyzing the DJI Flamewheel 450 model. For our first iteration, we decided to go with a fully solid arm extending from the center chassis made out of ABS plastic. We then moved to a design with rectangular cutouts for weight savings, as well as maintaining the structural integrity of the arms, and it is still made out of ABS plastic. Next, we moved to the final design of the actual product with triangular cutouts, except with arms made out of ABS plastic instead of the original material that DJI went with. Finally, we tested if the arms were made out of 6063 aluminum to view if the stronger material would help the product. Some of the analysis that we performed on the quadcopter were structural, modal, and fatigue, using the SolidWorks simulation program. Here we have the structural analysis results, which shows the max stresses, max displacements, and weight for each iteration. We ultimately have decided to pick the third iteration, which is the triangular cuts made with ABS plastics due to the weight of the plastic. The lower weight of the material benefits the quadcopter for its aerodynamics as well as its battery efficiency. This iteration contains the highest stress with 8.81 MPa. However, the factor of safety for this iteration is 5.5, making these stresses negligible as they will be the max that the quadcopter will see. It also has the most displacement. With a 4.6 millimeter displacement, it is not big enough to worry about. After our structural analysis, we decided to perform a nonlinear analysis to evaluate whether our results from the structural analysis were accurate or had any discrepancies. Here we see that the nonlinear analysis matched up with our static analysis under similar boundary and load conditions. The graph on the right shows the stresses increasing from the motor mount all the way to the inner chassis plate. We also see a drop in stress when we reach the chassis plate. Next is our frequency analysis, which shows us the natural frequency of each design and the way the arms will move under the specific natural frequencies. Under these natural frequencies, the movement of the arms may disrupt the movement of the actual quadcopter. After our modal analysis, we took a look at the SN curve of ABS plastic with the stresses that we calculated and for the industry standard amount of duty cycles to test the product. We are able to say that after 250,000 cycles, our range of stresses will still be below the stress amplitude of the SN curve. Thus, our quadcopter will not fully deteriorate. To compare our closed form solutions to the values from the SolidWorks simulation, we calculated the max stress and displacement with our boundary and load conditions. We see that the error between the simulation and the equations given in class is large, and this could be from an error in our boundary and load conditions. Finally, we performed a fatigue analysis to view the percent damage that the arms would endure. With the results of our structural analysis and a 1 million cycle test, we found that the quadcopter will only withstand a 10% damage on the arms. This concludes our summary of our presentation, and thank you so much for your time.